Hello and welcome to the 10th lecture of the Deep Learning course. Today we're going to be discussing generative adversarial networks. Generative adversarial networks are one of the most popular families of generative models, especially for their ability to generate images of very, very high quality. So in today's lecture we're going to be discussing four items. First, we're going to discuss a bit of some motivation behind implicit density functions. Then we're going to give a brief introduction to generative adversarial networks and their mechanics. We're going to discuss some of the challenges that we have to face when working with generative adversarial networks, and of course these are open questions and ways, they show ways of how we can improve generative adversarial networks in the future. And last, we're going to discuss some GAN model variants and some modern architectures that either solve some of these challenges or they produce really, really high quality results. So in our tree of our generative models, GANs situate themselves on the implicit density function subtree. So why is that? What's the point? So we've seen that in our generative models so far, the main goal is to explicitly model our density functions, our P of x or P of z and x, and usually this is for one reason or the other intractable. More often than not because of the normalization constant. Specifically, the normalization constant has to integrate over an exponential number of summands in case of in discrete case, or in the continuous case it has to solve for an integral, which more often than not is analytically not possible to solve. The way of circumventing this problem is usually via very intelligent approximations. So Boltzmann machines have energy functions and they've got contrastive divergence to address this problem. Variational autoencoders rely on variational inference and approximations thereof. And the question that is posed by models like GANs is, do we really need an explicit density function to begin with? Do we need to know what is our P of x or an approximation of it? Do we need a P of x comma z? What if we're just interested in actually making generations, not a density function per se? So with an implicit function, we no longer try to directly optimize either P of x or P of x together with some latent factors z. Instead, we learn to evaluate directly if the generations are plausible. Does my model produce samples, images, most of the times for GANs, that look like real or not? And if the generated samples are not realistic, if they're not plausible, then we would have to somehow return gradients to correct the generative mechanism. Of course, the question here is, what is a plausible generation, especially in an unsupervised setting with no guidance? We basically give the model the data, and this is it. So we have to figure out a way we can inform the model, the generative model, whether it does a good job or not. And for generative adversarial networks, plausible generation is or checking whether the generation is plausible is simply by having an extra competitive neural network that tries to figure out whether the generations are indeed real or not. Thank you. This approach works really well, and generative adversarial networks were first proposed back in 2014. By now, the progress is really outstanding. So whereas the original paper was focusing on simple pictures like MNIST or CIFAR maybe, Nowadays, tech giants like Nvidia produce papers and produce architectures that, believe it or not, generate pictures like those in the slide. Thank you.